today. So today to have Professor Bing Wu from the Santiago de Compostela University. His main research area is the high energy and the nuclear physics. He has very important works, which advance understanding of how the processes in heavy applications and like how the Coulomb system gets stabilized and how the hydrodynamic behavior emerges and how to describe the so-called plasma systems. So I'd like to have him to tell us the stabilization of Coulomb matter. Please.
Okay, thank you, Xu. First, I would like to thank the organizer for the invitation to this really nice summer school. And turnover. So I just want to thank the organizer for the invitation. So it's a really nice summer school. Actually, I also learned. Okay, so my lecture will be the last, but my lecture will be like for Hanwan evolutions, like in Zhang Yu's talk and Derek's talk, and also actually Professor Leo talk about late time behavior and how the more like hydrodynamic behavior or final state build up the flow. But I'm going to talk about what happens after you collide nuclei or maybe smaller. Then what happens right after the collision. So so you see what the contents here. I'm going to talk about some fundamental things. I want to give you some picture or the general discussion about real-time dynamics in quantum field theory, specifically in QCD. Then I will talk about like and the classical field approximation and the quasi-particles. Quasi-particles is basically the Boltzmann equation. Then this will be my first lecture. Then the second one, I will talk about the applications, just how to solve the kinetic theory, then what we made. Okay, so let's start. Somehow it does. So let's just see, actually, I think you have already learned this in several other lectures, but I want to set up my convention. So here we know the QCD is really beautiful theory, and it only has two parts. You have the Coulomb part, you have this quark part, which Coulombs through these so-called covariant derivatives. Then, so in real time, we have the color NC equals 3, and the color structure, or so-called Casimir operators, you will see, which is basically the effective color charge for Coulombs, and this CF, which is the effective color charge for quarks. Then, so you have also seen this before. So the QCD, then after renormalization, you need to introduce some renormalization scale. So denoted by mu here. Then you renormalize coupling is running, meaning it depends on this mu. Then what you need to do in perturbation theory is just you calculate the beta function order by order, and so here I just give you the lowest two orders. Then as long as you have beta functions, you can really calculate the running coupling. You're running coupling with the data, so it fits the experimental results fits the theoretical prediction very well. Then of course this is mainly because if you go to the large moment scale, size becomes smaller. So this is called the asymptotic freedom. Then actually the mean uncertainty in our fields is actually from the non-productive physics, right? So you see uncertainties in several phenomenological discussions. Then so mention these lambda parameters. Here I just give you the precise definition. So as long as you have beta functions, then you just integrate the inverse of this beta function over this alpha s, then from some alpha s q up to infinity. Then on the left-hand side, actually where this lambda parameter comes in, usually we call it a lambda QCD. Then so basically this tells us if you Q go down to lambda alpha s will go down to infinity. But this doesn't mean your alpha s is really infinity, right? If you can do the lattice calculation, then you may determine what's the alpha s at lambda QCD, the scale at lambda QCD. But this it just tell you if you use productive results, you will get infinite coupling at this point. Then obviously your productive calculation breaks down. And usually this lambda QCD is quoted like 200 MeV, as everybody knows, which is the inverse of the proton size. And one has to be careful if you want to do some precise things. Actually, this lambda also depends on the renormalization schemes, etc. But here I just want to quote this number because I will try to stay in perturbative regime, meaning all the virtualities or hard scales will be larger than lambda QCD. Then let's see what's the reality. So actually, you have seen this picture in several places. Is potentially 1 momentum GeV. So, but it's order 1 GeV. Goes on the mid rapidity, it's just the pseudo rapidity equals 0. So then to estimate how many particles are produced in central lead-lead collision. Then use how the scale invariance, you can have the estimate like the number given by the atomic number of the colliding nuclei times. In this way, you can get the multiplicity in the hypothesis could be that you can determine precisely. Then using this fact and also in it has some dependence on A, but the change returns which for the have these two numbers, you know what's the energy density you look at. Then actually, I think this is the Heng Tong's work, possibly. I think it is. Then in lattice QCD, you can really carry out first principle calculation for the equation of state if you mu b equals 0. So this is really non-perturbative region. Then you can really, here it shows all the physical quantities like energy density, entropy density, pressure, etc. in terms of this temperature. Then if we put this density here, you will see actually this gives us some temperature of order 300. Then of course, so all the physics, if we talk about thermalization, obviously we start from higher than this 300 MeV, but obviously the process is borderlining between difficulty in this field, right? So this gives, I think, some uncertainties for many predictions. Then here, just for your knowledge, so why for this kind of properties, yeah, the thermal equilibrium properties, why is not so, why if you look at the partition function and in the path integral, you have this exponent, you have minus sign here. And actually, the action in Euclidean space usually is not negative. In this case, really, there's no, technical difficulty. So I just see, starting from some initial condition, how the system will converge in this plot. Okay, so then not really equilibrium unless we use Jean-Yves picture. Okay, you may be in thermal equilibrium, but for this, so we know at a late time, so one can use hydro. After the collision and before the hydro is valid, then this stage actually you have to do the calculation from Qcd, but it's really non-particle physics. It's really many relativistic many-body system, quantum system. It's a really hard problem. If it's non-perturbative, it's the open question. So because the so-called sum problem, then actually this is the invention of our community. So we call the process starting from this collision time, then up to this hydro. The time you can use hydro, we invent some terminology called hydrodynamization. So what's the sum problem? It's not so hard to explain. So as I show you, if you calculate the static partition functions, you have this minus sign. We usually say you are doing the calculation in imaginary time. You will see later. So actually, you will have path integral like this one. So instead of minus sign, you will get action in Minkowski space. Then this S can be positive or negative. So the traditional, conventional lattice QCD cannot yet use this kind of calculation. Then of course, like in Professor Ho's lectures, so he talked about the gases. Since we don't know how to deal with the strong coupling, then you may use this. In this case, for thermalization, actually, you just need to study the formation of a and one can see the thermalization in this strongly coupled system. So you get I saw some of your solution, but of course, it's still a long way to go. So recently, you see the really rapid development in hardware. So for example, the IBM has some let's call quantum processor, which has more than 1,000 qubits. Then they have some really ambitious roadmap. Then actually, but the technical difficulty is we are still in so-called NISQ era. So N stands noisy. It's basically different quantum system. So there's the environments. Then you don't exactly get what you want. So there are always some which actually, at least for those machines, there's no error. Reduction. So you don't really get precise what you want. Then also there's only 1,000 qubits. So if you look at QCD calculation, actually way more qubits you need to really achieve the same precision. We do actually ever focus on the thing we know. So we want to go to the higher. We can use perturbative method to derive some I show you, then you can avoid some problem. Okay, so somehow let's talk about these PDFs. I just start with from here. So basically, what we imagine we then if the collision energy is high, also the tip, then you would imagine initially this system which up. So then we know the PDF is in this equation one only considers 1-to-2 splitting. So what happens is if you look at the small x, the part split into 2, then since number of gluons at small s. At a different scale, of course, you have different number, but all the picture is if you go down to small enough f, you always has a large contribution. And here I can do some so-called leading log approximation. It's usual function. Of course, you have square root of log x here. So inside the proton or nuclei, let's first consider proton. So a lot of gluons, where should they go? So if they encounter, they have to emerge. I think this is accepted. Actually, breaks down. So you have to think, okay, called gluon saturation. So if the 1-to-2 and 2-to-1 establish some kind of equilibration, not the equilibration we are going to talk about, then you get some saturated distribution of gluons. The gluon number shouldn't go infinitely. So one can really do some quantitative calculation using so-called color glass condensate. So this is an effective field theory. Actually, you just take the large S part, you integrate out the large S part, then you get some effective small s. And here, as I just mentioned, for example, in this plot, so if you go to large x, at the scale, actually, any moment scale, if you go to large x, so you just get the standard PDF. But if you go to small s, what is expected, actually the gluon will eventually saturate. When I say saturate, actually the distribution in sense. Then, so actually there is a line is called QS, which and the dense region. So this QS is the saturation momentum. So this saturation calculate for spherical nuclei. Nucleus. In this case, actually the QS squared by order you consider, then the length of the medium, then the density. This is the normal nuclear density, then the times the gluon distribution for nucleon. So at the LC, we square. This means QS of order 2 GeV. Then you do is to take the limit that QS is large enough, the non-perturbative effects, or the contribution. So in this case, actually one can also operate right after the collision. So we use the previous formula, then we know. Then from this one, if you think about the definition of gluon distribution given by etc., then it's proportional to a squared at the leading order. So this just means like OQS large enough. Actually, G is weak coupling in this case. actually you have one thing you need to consider. Then what would be the picture? I think I will also discuss this long details. So here I just should basically show in this tau. Tau is the environment. In fact, you have not seen the number. I see what these two tools are and how we can derive them. So this is yeah, it's really just I just want to give you some basic stuff about so-called non-equilibrium quantum field theory, because yeah, some of you want to do some position useful if you start here. But if I give you kinetic theory, then so figure out what you do, for example, in quantum computing, then you need to come back here. Right? So if you want to study the evolution of the system, you need the evolution operator, just equivalent to the say the called. Actually, you can define some path integral in this way. So if you remember the path integral defined quantum mechanics, this is basically the same. The only difference is called field by the field. Yeah. So this phi could be just, so in order to really study the evolution of the system, so what you know the system, the matter in your system. Then what you need is at the initial time. So now let's say initial time equals 0. For example, it could be the energy moment tensor. Observable. So you just take the trace of this observable times the density matrix at a later time. Then of course this density matrix will be evolved according to this formula. You have U dagger, then you just write this U and U dagger according to its definition. So in this way, actually, well, here I also insert some trace. So you see this d phi 0, d phi t. This just take the trace. Then, so what you get, actually, you have this one. Since you have U and U dagger, you need to introduce two fields. One I just called phi plus, the other phi minus. But they are dummy variables, right? Because you need to integrate them out. Then, so if your exponential functions are just functions, right? You can combine them. Then if you combine them and you will get piece, actually look like your evolution operator, right? So in principle, actually, if you want to study non-equilibrium, so actually and control of 0 is something now with doubled number of fields. Then you can do everything you know in quantum field theory. So that's basically what's the the Schmidt-Caudish formalism, right, in this language. Okay, so for the discussion, so I'm going to use so-called phi 1 and phi 2 fields. Phi 1 because now theory with two fields, phi plus, phi minus, then you are free to make any transformation, right? So I want to say, okay, I define the difference of these fields. Then I define phi 2 is the average, just for you to remember, to memorize. The 2 is larger than 1, so So actually, phi2 fields you will see is always larger than phi1 fields. So phi2 is the phi1 actually is the quantum fluctuation. Okay, then go to QCD. Then of course we have to replace these and gluons. Then you have this kind of more complicated thing because now you double the number. I just denote the A2 by A and the A1 plus A minus equals eta. So then the other thing, of course, if you want to do a method, so you need propagator. So and this means you have 4 propagators instead of 1. But transformation of fields, actually you will see this 4 by and this is because there are some relations among the one advanced Green functions. The other one is the retarded Green functions, as you studied in like classical electrodynamics, etc. Then here, actually, the two components of this propagator is really onshore condition, but it's negative energy. You will see why, but actually that's what's needed for the derivation. Okay, basically, if you can solve what I say there, so basically you get, well, you can study any necessarily for non-equilibrium, but this is general. Basically, that's what you need to evaluate. But as we see, so you has some problem. Then in some limit, actually, you'll see you can integrate out this path integral. But if you put it on lattice, you will have problem, at least for what we see there. So you have really huge number of gluons to use classical field approximation. One can, let me say this way. One can use
these RD bases.
in the other literature. Call it right, but right. As I told you, so in the reference I read somehow. So now actually, in order to see how you get classical field approximation, or usually people call it classical statistical approximation. Actually, this was used by Derek, right? In his old calculation, he just solved the classical field. Then basically now we use that. So in this so-called enlarged quantum field theory, so you have 2 fields. Then if you write it phi1 and phi2, then you get this form. I mean, it's a kind of trivial. You just insert definition. You get relate any observable as we give in the general form, but now we just replace the Lagrangian. Then you get this one. So what I want to emphasize is, if you want to study is large, in this case, actually, the second term, so I call the quantum vortex, can be interpreted with quantum fluctuation. Then you basically drop. So I just first give you the answer. So what you will see then if you want to calculate any observable, what you only need phi 0. So this phi 0 give you the initial condition derivative of classical field. Then this so then after you get the class time, then you average that use explicit formula. Then forward drop the cube. Then you only have this linear term in phi 1. Then if a linear, I mean this functional, right? So the functional in this path integral. Then this actually just classical equation. Then you can integrate out phi 2, but here you have Jacobian. You need that Jacobian such that you convert the boundary condition at phi 2 at phi in the phi dot, the time derivative of this field. So that's kind of magic, but if you work, let's use for this so-called classical statistical approximation. So here, but the so we find is since start from here, you can study its UV behavior, right? You calculate loop diagram just like the textbook calculation. What you find is you find UV divergences. But what is actually, well, maybe not surprise, right? It's classical. Then this UV divergence is form, and you need to introduce some additional term to cancel these UV divergences. And also it's non-local. So it's how to remove the UV divergence systematically. What it means is just if you time at some point, actually your results will totally determine the UV cut Qcd. So you have some lattice spacing. This the inverse of this one. Some standard thing. You need to put in some maximum, right? Determined by those parameters. So you cannot really go to late time. So and do the same approximation in Boltzmann equation. This means you neglect some then for distribution goes like this one. So F will given by T. Obviously, the energy density will be of lambda UV. Then since energy is determined by the initial energy density and also this UV cutoff. And yeah, that's the problem. So you can use it for early time, but you cannot use this one for what we are going to talk about, like a thermalization. Then, so now we still have this quantum field theory, right? What from quantum field theory, then you can do some approximation, see whether you can get the standard knowledge. So the first I want to mention, actually also like in professor, so actually people use kinetic theory or transport theory a lot. Then here what's the limitation? But if for Haiwan physics, because mostly preserve physics check because it's hard to justify. But for phenomenological study, it's good. But you can check, okay, what you can derive here. Then or net theory. So start from something called Dyson-Schwinger equation. So you studied stuff. If you want to calculate the propagator, right? You need number this equation. So this basically, yeah, just then you need to go to two loops. This diagram. So the cell gives you effects for multiple scheduling in sense. So this equation just really sum over all the possible manipulate the Dyson-Schwinger equation I showed you before. Then here approximation, you already have to assume this x is the average. This is like a weak. So 2-point correlation function, S is the average of these two coordinates. Then you can do. Then the next thing is the crucial thing. It's called quasi-particle approximation. Usually you don't exactly get this form in quantum field theory, but as long as the response, yeah, as these two professors mentioned, corrections, but the mean correction comes from G2. Then has this for the free one, but the medium effect could has positive or negative energy. Then as long as you accept this approximation, then you can go. You can calculate the self energy. So at two loop, you need two loop to get 2 to 2 scheduling actually. So yeah, you have this pi 1 1, you have this pi 2 2, and I think I have some cut here. When I say cut, this means 2 2. In 2 2, you have energy, negative energy. Then, but if you combine them, because the kinetic constant, actually you can only pick a negative energy. If it's negative energy, it means the incoming. If it's what I say. So if it's positive, then it's outgoing, etc. But you have two different choices. Then actually, after you combine them, you use kinetic theory like this. So that's actually what you use, right? But I just give you, okay, you can derive this one, accept some approximation. Then in principle, you can do the same. This actually also I formalism, etc. Then here I want to comment, okay, so you can derive this one. But actually quantum field theory obviously is richer, as I told you. So this Boltzmann equation is from the quantum field theory. When I say quantum field theory, I just means the past integral, etc. I showed you before.
As you said, yeah, the uniformism looks like a 2pi, but of course, 2pi looks like a quantum distribution process, right? Where do you make a...
You also get those equation in 2pi instance. I mean the Dyson-Schwinger equation. 2pi for the self energy. You have for 2pi you need 2pi, exact 2pi, right? But it just I don't use that language. I'll show you one example, right? So what you can do is, okay, let's collide to then you have radiation, then you calculate the radiation, you use this radiation to calculate G22. What we get is something like this one. I mean, this is not only like this. If you do in quantum field, in thermal field theory, you may also calculate. You will see. I mean, the picture is similar. You will have some function. In this function, you will have really dominant contribution. And p squared equals 0 in this case, because I assume it's massless. So indeed, you will get some you will dominant phase space, but actually you don't exactly get the function. But as long as this function is large enough, so you basically can replace this complicated shape by the function. So let's the approximation. Okay, so this principle you can include like inelastic kernel, etc.
You said the ultraviolet that I know that difference, so that is the case if you number of type spectrum, power law spectrum, right? And if that you get state, right? So is there any
so if you get this self-similar solution, then you can cut to step.
Yeah, but that is a little bit naive, right? I mean, the question is whether the integrated is sensitive to the UV cutoff or not, right? And so if even if the function at the power law page, if the power is sufficiently large, then the integrated quantity.
Right. That's what I'm saying. So usually for this self-similar solution, it look like a Gaussian tail or something. So there will be separation. Usually there are separation at a large p. Only usually with this they will have like a separation tail. It could be power law, but yeah. But when this power law behavior, reach the UV cutoff, it will stop. Then eventually it will fill this thermal distribution. The important, before this tail reach the cutoff. But if it's a self-same solution, you know what's the shape, right? Then use that shape. You know when this self-same solution, this tail reach the UV cutoff. Actually, what's into precisely lambda u. So because when I say the classical approximation, the UA part, the IR part is always okay, but f, the distribution function, all this approximation is correct if your f is larger than 1. But if you have self-similar solution, because the conservation number, for example, so at a later time, actually f will draw below criteria when you should stop. But for this self-similar solution is always a solution. So you approximate your Poisson equation, you keep the f cube term, it's always a solution. But you have to stop when it's drop. This self-similar solution is not destroyed by this UV cutoff. So when this UV cutoff will come in your solution, will change your solution. Okay, good. Right, but now just I want to show you what's the equation. So how? Okay, so I think can finish. 222 principle, you can include 223, 224, etc. But actually, you don't need to include everything. We can also talk about the coupling expansion, right? But when we discuss about coupling expansion, actually you have to be careful. It doesn't mean you just look at the amplitude squared in the vacuum, then you count the number, because in the collision kernel there are also some contribution from phase space and change your power counting. So then I will explain to you later. But the when we say the leading order Boltzmann equation, so we definitely need to include, but actually also 1 to 2 contribute. When I say 1 to 2, imagine you have 2 to 3 process, right? But I guess when your instruction in this sense you have 1 to 2, but yeah. So then here, so just for simplicity, we actually also use something called the diffusion. I just called it's beta, stands for the Boltzmann equation in diffusion approximation. Diffusion approximation, imagine, I mean, even in plus in minus, if you check the differential cross section, actually you at the forward. So this just means so actually the total cross section is dominated by small. You only keep those dominant contributions. This is the diffusion approximation, and you that logarithmic terms. And if you keep the logarithmic terms, actually you can see like this one. So this is something called the Fokker-Planck equation, but the have some correction at the distribution function. And so yeah, have a back term, etc. So here in this equation, there are two coefficients. Is given by Q hat divided by MD squared. What's the physical meaning of those coefficients? I repeat this diffusion approximation again. So just imagine you have then so this Q actually much smaller than the momentum in this P prime. So after that, you can diffusion approximation. Then the MD are the plasma. Then actually, if you stay away from the charge, you cannot see the charge because it will polarize the medium, and actually the range of this charge is infinite animal. So you cannot. So this is the screening. This is called screening effect, and the typical length given by the mass. So this is the same in the plasma. You also have similar, but actually this definition actually is exactly the same as the medium, but the distribution here are non-equilibrium. So you have section now for this 2 to 2 scattering will goes like alpha s squared more or less. like the geometry is important. Code here one has 1 plus f, 1 minus f because the quantum effect. So you have some statistical factors. Right. Then, so I think the important knowledge you need to know is just the meaning of this Q hat. So this Q hat basically it's just the transverse moment squared per unit path length. So if I have actually the transverse momentum is 0, then it will go through a medium. So its momentum run walk, right? It will receive some transverse momentum. So here T basically just plays the role of does not evolve rapidly with time. Then this is interesting because so we have this we call source term. Actually, yeah, I think the is not. Then so there's some source term here. It's just like a list diagram. If you grams in T or U, then if you only keep the logarithm term, you can integrate this or depends on whether it's quark or gluons. Then it looks like quark into gluons, but you still have the conservation of numbers because from the medium. So since you are dealing with the whole system, you still have the conservation. The 1 to 2. So actually, so if you have like gluons, it will split into two gluons, big lab evolution equation. But the difference is you don't actually they are factorized out from some a process with a large number of collisions. It just the other collisions becomes the transport coefficient, etc., to enters the emission rate of those processes. Right. So you're just thinking about like one onshore particle becomes two onshore particle, but what during this emission actually is given by the splitting rate. So here it's just like you generate like a 2 to 2 thing to 1 to 2 thing, you put it in the F and then 1 plus minus F in the final state, etc. The main thing is what's the splitting rate. So here you consider 2 to 2 process. Now you consider the collinear limit. So I mean this is also what you do, right? In traditional QCD. Then in this case, actually, the process will factorize this. This actually just the cross section for 2 to 2 gathering, just like the vacuum splitting, like the Galab evolution equation. Then you have additional RFS for this emission vortex. But the thing actually there's a phase space like this one, dp, d3p, fp, 1 plus f. Then for this distribution, we denoted by q. Then we know this will give q section, the 2 to 2 cross section, elastic cross section, as I told you. I had to use the previous formula to calculate. Then MD square actually given by alpha s. Them together, because this MD square corresponds to alpha s. So 2 to becomes square order. So this is the same as 2 to 2. General so-called MPM effect, etc. as no 1 to 2 kernel is the same order as the 2 to 2 kernel. They are also of order alpha s squared. So you have to consider it. Okay, then here I just show you what we do. We do the LPM effect because the energy loss from effect proportional to T square at later time dominate effect. So we will keep the LPM effect. Okay, just summarize a little bit. So now we have the kinetic equation we call beta, which include 2 to 2 kernel. Then this 2 to 2 kernel conserves the for each quark flavor. I mean because QCD. Then the total energy it has to be conserved. Then consider 2 to 2. Actually, the total particle number conserved because as you see, gluons can become quarks, right? QQ bar you have to conserve. But yeah, so you conserve the total particle number. Want to conserve this net quark number for each flavor, then the total energy, but the number beta is the whole equation. The whole set of equation will conserve the net energy. Number will give you some a chemical potential, right? That's why I mentioned this one. Then actually the beta, or yeah, or if you replace a D is useful. So I think I will stop here for the first lecture.
Thank you for the very nice lecture.
So it's clear or too complex?
Yeah. Is that 2 to 3 is the same order? So
2 to 3 is the same order as 2 to 1, but in this collinear limit. It doesn't mean in general. Also, you have a single scattering, you have one emission.
Nice lecture, I enjoyed it. I have a very basic question. You say that gluons is the same thing as a classical field.
Right.
I understand that a classical first statement true. I mean, a classical field is a coherent state.
Right.
It's not necessarily a coherent state, so
Basis. I can also coherent field. I use this.
用的 personality state saturated. And so that it existing
Nothing. So I was in equation. You get
function
okay.
Question.
stabilization is emphasized. In this at the initial time period. So the first I told you about diffusion. Go the small if large collision small angle scattering. So imagine you have collision of two protons. Then if you have some physical which is much larger than QCD, actually you can convert the collision of protons into collision of quarks or gluons, right? Then, but the problem is, so for the large X parton, including the valence quark, so-called valence quark actually is the difference of the, for example, U quark and the U bar quark distribution. So that's called the valence quark. Then you will see the distribution mostly peaked at larger X. So in this case, actually larger X parton and the valence quark will mostly travel along the beam pipe after the collision. So they will carry away a large portion of collision energy and also the baryon number. So here, of course, really high enough collision. But if you look at the previous data, so here, for example, you have low energy experiments, AGS, etc. Then you go to RIC. Then you will see there's some decrease of the net protons produced in the mid rapidity, y equals 0. So that's the picture I want to say. So this just means at the higher and higher energy, actually perturbative picture becomes more and more reliable, right? So basically we'll start from here. And the other information we need is so-called the longitudinal boost invariance. This also John Yu also mentioned. So this actually can dated back to Bialken. So this actually really from perturbative QCD. And if I told you about this collision of the hard or large X partons, then after they collide, they will basically travel along the beam pipe, but there will be some T-channel exchange. Then actually they can radiate. So the radiation of those soft gluons, so we know the soft gluon radiation is factorized out from the hard process or from the rest of the diagram. Then the soft spectrum, I mean, is basically given omega di. The omega is basically given by a constant of s times some logarithmic divergence. Then so di omega used to be d omega here, actually is just di eta. This is the rapidity. So actually from perturbative QCD, it's really easy to understand why you have this longitudinal boost invariance. Then of course in CGC picture, then you can make more quantitative studies. See this omega is about the QS. Actually in Bialken's original argument, so he basically assumed the soft parton has an energy about the lambda QCD. But the origin is the same. So now selection we need. So the first information, as I told you, actually most valence quarks and large X partons actually will not be stopped at the mid rapidity. That's why if you check the energy of your produced QGP, it's much slower than you can expect it from the collision energy. Then the second is just okay, there are almost no baryon numbers at high energy. So then our initial condition is just okay, we have some gluons, and this gluon has some F0, which is parameter for us, then it could be an input from CGC. Then of course, for simplicity, we just use step function. It's just mimic the saturation of gluons. Then there's no quarks. So here we just call the gluon distribution F. Then the capital F stands for the quark distribution, and the F bar stands for the anti-quark distribution. Then, so they are all 0 initially. So what we want to do is we want to study thermalization and also see how the quarks are produced. And as I mentioned before, so the set of the equation with our beta, just a Boltzmann equation in diffusion approximation. So actually, for switch off the expansion, let's give you some complication. So in this case, so one thing you can check, actually, you have this set of equation, right? Then you can check, okay, what happens at the small p? If your p go down to 0, so what's the behavior you can get from the equation? So that's usually what we do, right? Even though we want to do numerical calculations, but we can do some analytic calculation to some limit. And what you see actually is kind of surprising. You just, as I mentioned, you have 2 to 2 kernel, you have 1 to 2 kernel. But actually for p goes down to 0, actually 1 to 2 kernel is dominate in the sense that if you check the power of the momentum here, so actually the power from 2 to 2 will be smaller. So I mean in denominator in this sense. So if p goes to 0, so it's dominated by 1 to 2. Then so from this one actually you see some kind of distribution, thermal distribution. If you remember for quarks or gluons, then you have some conserved number. So this actually exactly like a thermal distribution with p equals 0 for quarks and antiquarks with some chemical potential. Then here, this p times f actually basically given by t star. This also like a thermal distribution, the Bose-Einstein distribution for p equals 0 behavior. Right? So that's what I say here. Then here I just want to show you again. Actually, I showed you this. So the t star actually just given by q hat divided by alpha s and c. This logarithmic divergence then times md squared. So if you go to a thermal distribution, this t star is the standard t, the thermal equilibrium temperature. Then the same thing. So we find we can also define some mu star. Then this mu star is actually given by the ratio of this IC bar. These are the coefficients for the conversion process. You have gluons, then this gluon could become quark, etc. So then the other one is for the antiquark. So this actually give you the, I mean, if you again in the thermal equilibrium case, if you have some baryon number asymmetry, then actually you also have this mu. The mu is exactly the same as this mu if you use thermal distribution. Okay, so now as I told you, so we start with the initial distribution such that the quarks and the antiquarks are missing. Then since the equation respect to the symmetry of quark and antiquark, actually this means the quark distribution and gluon distribution will be the same, and all the flavor quarks will have the same distribution. Then if you have this symmetry, of course, IC will equal to IC bar, then of course mu will be 0, right? Because the chemical potential tells you the net number of quarks. Since the net number of quarks is 0, of course you get 0. Then in this case, actually the whole evolution is really just kind of determined by the q hat and md squared. So you only need to know these 2 parameters, then you can know what happens in the system. Okay, so let's start with some initially overpopulated system, as I told you. So initially you would expect you produce a lot of gluons. Actually, this picture is independent of CGC, right? If you look at PDF, it's also true. But what CGC tells us, not only that one. Actually, you may do some perturbed calculation since those gluons will have typical momentum of outer QS. If QS much larger than lambda QCD, so actually you would expect the corrections from non-perturbed physics is small, right? Okay, so let's just as I say, so we first studied overpopulated case. This just try to mimic the initial stage of the collision. Then there was some intuitive discussion, I think already possibly 10 years already. So when I was a postdoc, so there was discussion. It's just whether, I mean, if you have really highly populated system of gluons, then what should those gluons will become some Bose-Einstein condensate? So let's people have some discussion. Then I think the answer now we have is no. You'll see why, but there shouldn't be formation of BEC even transiently. So there's no need to form BEC. It's just the 122 kernel will actually remove all the extra gluons. So when we say overpopulated, this just means there are more gluons than the thermal system with the same energy density. Then let me just illustrate you why. Actually, I kind of tell you part of the answer. So if actually this issue actually starts from the calculation from 222 kernel. So if you start from 222 kernel, then at that time, I didn't have time to put the paper there. So they find, okay, at some point, if you only use 222 kernel, then if you have too many gluons, at that time, numerically, you cannot get any solution. So you just there's some numerical instability, then they think, okay, since there formation, then actually found at this diffusion equation in this form. So you see the left-hand side here, if you calculate the number, so actually that number is simply given the boundary condition of the p squared times Ta. So you have one boundary from p equals infinity, then the other boundary p equals 0. Of course, I mean for p equals infinity, because your distribution always almost exponentially surprised. So it's always 0. But at p equals 0, actually this p squared times Ja actually defined this way here. It's not always 0. I mean, actually you can see simply here, because if Fa goes like T divided by P, or goes like 1 over P, actually you will see this is not 0 anymore. So it's just at P equals 0, actually, if your F goes like 1 over P, I'm finding a number at P equals 0. So of course, the natural interpretation is, okay, this is a BC, right? So yeah, to summarize, it's just if you get this from this one. So actually, if this P times Fg minus T star is not equal to 0, this actually what we find if you only have 222 kernel. Then actually, in simulation, you will see there's some gluons will go down to P equals 0. Then the number density is not 0. So but what we find now is, okay, so as I already showed you, right? So actually this is the case, right? So you have the P times Fg go to the T star when P goes to 0. Then actually, so somehow the nature or this side equation knows if you have extra gluons, so they don't have to put it P equals 0. They actually, as long as this gluon want to go down to P equals 0, actually the 122 kernel will just take it away. So such that is not 0. There's no gluon accumulation at P equals 0 or the BC. Okay, then, well, this of course, I mean, it's interesting, right? Because we learn about this BC concept, etc. But that's obviously not something we can really measure. But now let's say something is more relevant for let's standard picture so about this thermalization or hydrodynamization, etc. So now let's say, okay, we have the F0 much larger, much larger than 1. Then, so what we find is thermalization proceeds in 2 stages. So the first stage, of course, you could imagine, right? You have some distribution initially, as I give you this step function. But if you calculate number, actually you see the number, most gluons will have a typical momentum of outer Q. I think, yeah, that's the point. Maybe we need to use the whiteboard here. No, you just, I think it's trivial point, but usually because I think based on my understanding, so in our educational system, we don't usually do a lot of parametric estimate. So I think that's why that's the point. Yeah, I show you something, right? So you can trivial, right? Because for example, we have this distribution, something like then what's really the number, right? So we estimate the number, so the number density. So basically something like F0 Q P minus. So because of this factor, right? So typically, actually, the typical gluon number actually, the typical gluons actually carry a momentum of about the. I mean, because this one, so this actually means typical gluons will all the gluon number will mostly dominated by large p, right? This is constant now. So basically, in our case, this just equals p0, then from 0 up to q. So because of this factor, this is constant. So actually, this integrand, the whole thing actually dominated by large p, right? The largest p actually gives q squared. So even though this one, it looks like you have gluons go down to p equals 0, but actually what really happens is the whole system is dominated by hard gluons. When I say hard gluons, it's just gluons which carry the momentum of other q. Then, so since the 2-to-2 scheduling and 1-to-2 scheduling both take time, right? So you think about the physical process, so it takes time. Then as long as they don't generate enough soft gluons or other partons, so actually all these properties shouldn't change much. So I usually use this tilde. Actually, this is also standard way to do parametric estimate in so-called bottom-up paper. I will show you later. So all these quantities, but change really slowly. I mean, parametrically, you just say, okay, we neglect the corrections to those because they are subleading. So in this F0 go to infinity limit. Then the first stage is just okay. So the corrections to all these quantities is small. But you think about physics, right? So now we have I told you, so there's a Q head, right, in the system. Then at some time, actually, each parton will receive a broadening of order square root of Q hat times T. So I show you the formula, actually it's here in this line. So this P squared goes like Q hat T. So from this one, you can estimate, so how much the momentum of each parton is changed by multiple schedulings. Then actually you will see, because this formula, so at this stage, at Q head, you can go back to the definition. Then you basically replace by the momentum integration by the power of Q. Then if you insert here, you will see at this time. So if you plug in this formula here and Q head plug in here, you will see at this time, actually the momentum broadening, the momentum you got from multiple scattering will equals Q. So what it says at a late time, actually, typically, if you imagine you have one particle, you put it in water. At a late time, it has a larger momentum, right? Because the random kick. Then actually, after t larger than this value, so actually the random kick will give you contribution to the momentum of those gluons larger than its initial momentum, which of other q. So in this case, actually, because the energy conservation, right? Now the number of of gluons has to decrease, right? Otherwise, energy is not conserved. So actually, that's what happens in the second stage. So basically, you have momentum broadening, then the number has to reduce. Then either if you only have 2 to 2, then you have to put it in BC because momentum equals 0. It does not contribute to the energy. But if you have 1 to 2, so this means there's recombination process. So, but they are not so important. So everything actually can be determined by the momentum broadening. So then you just use these two relations. So you have these p squares of order q hat times t. Then you have energy given by the number of gluons times p. And initially the value is f0 q to the fourth, right? So that's because our initial distribution. Then you have to show the NQ consistently because Q hat also depends on NQ. NQ and so Q hat will be proportional NQ times F0. Well, I think it's better I show you the definition here, I guess. Yeah, let's go back a little bit. I think it's that's the part why I spent two days to prepare the lecture notes. I really don't know how to. I mean, it's a trivial stuff, but you just need some time or some people tell you how, what I want to do. So let's, it's here, right? You can see the Q. That's what I say. So this Q hat, then it will be proportional to F. This F, because in the first stage will just equals F0. Then this P, you see D P Q. So this will give you a phase factor Q, right? It will, I mean, you will have some constant, but actually the outer magnitude you have, because this integration, you will have Q to 3, Q1 Fg. That's what I'm talking about. So this one, so yeah. So the number, I think, is already here, right? You will have something like this one up to some constant, less of order 1. Well, let's put it exactly. So this is the number, right? But because this is constant for us, then actually this will get F0, right? But what's the so inversely, what this means? This means F0 equals n divided by q squared parametrically. Then your q hat just based on that definition. So you have alpha I squared by definition. Then you have the same piece like this one, but you have 1 plus fp, right? So this piece actually is the same as the number. So you just have the number. That's what I put here. But then you should have this F0, right? This F0, then this F0 should be equals ng divided by q, right? Q. Then, but I mean, this is for constant. But now imagine the typical momentum of the particle is something else. Now I mean, but parametrically have the same. This typical momentum will change. So you just basically replace by this pq by this p, this q by this p cube. This p is the typical momentum. So that's what I use in the parametric estimate. Yeah, I was debating how I say that, but anyway. So I hope you catch something, but it's not so. Yeah, I mean the algebra obviously is trivial. So if you have these two equations, you can just solve basically everything. You can for example solve ng based on these two equations. Then you can solve p. Then from those one you can get all the other quantities. Then you get this scaling behavior or transform. So I mean, it looks like really simple, this parametric estimate based on the phase space, etc. But you can really see from your calculations. And I think that's the magical part. That's the part I try to find a way to tell you, but yeah, I think it's hard for me to figure out how I do it. Anyway, so this is just purely based on the conservation of energy and also the momentum broadening from the Q hat. Then actually that kind of scaling behavior actually shows in our numerical results. Now we really solve, let's say, the equation. Then we use the initial condition. Actually, it's independent of the initial condition because this parametric estimate is really independent of the initial condition. And you'll see the scaling behavior. So on the right-hand side, actually, you will see the scaling behavior for the simulation with only elastic kernel, but we have to, as I told you, we have to put something in BC. Then this one is the results for the full beta equations. Then there's the elastic and inelastic. You see, they also obey this scaling solution. Then of course, so you may also see initially there's where the change is not so dramatic. Then at the later stage, so there's a evolution according to that kind of scaling. We got it from momentum broadening and energy conservation. So here actually there are some, this I think is a classical, as I told you. So there are some classical field approximation. Then they can do the simulation and they also find the same scaling solution. They usually call it a non-dimorphism point. But I think there's debate about this terminology. But the phenomenon is everywhere. Actually, this relates to the classical simulation I talked about actually before. Anyway, so then we can also do the same thing for quark production. Then here in the first stage, since everything is constant, right? So if your head is constant, MD is constant, then you think about the conversion term. So actually, basically the IC is also constant. Then obviously the quark production will be proportional to T, right? Because yeah, all the coefficient is constant, then that's the time derivative. Then at the late stage, actually, because the scaling behavior, well, you can just simply from the radiation formula or all this conversion term, you'll get the scaling for the second stage. You'll get this kind of behavior. Then of course, this actually, yeah, if you accept this kind of estimate, actually the algebra is really simple. But I think the magical thing is you can really check whether you have it or not from your simulation. So it looks like simple, right?
What are you plotting here?
No, this is the quark number. This is, you see, so you have the Golomb number, you have the T star defined by basically the Q height divided by MD square after some constant. Then you have the West-Green mass. Then you have the Q height, but divided by the dimension. So make them dimensionless. Then, because as I say, if you do the parametric estimate, you have barely change. Then you have another stage which should follow the scaling behavior because the momentum broadening and energy conservation. Then here basically we just the dashed line, actually the dashed line are just the curve, the scaling. So we just put the scaling and see whether they will follow the scaling or not. Right, that's yeah. Thank you for the question. Yeah, then for the quark we do the same. Then we can do the parametric estimate. Then there's a linear stage. Then actually at this stage we see the growth becomes slower. Then numerically it's well, it's quite close to the predicted scaling, right? In T. Okay.
At the end of the evolution, is the part number still very small compared to the Golomb number?
At the beginning, yes. At the end, actually, the quark number actually contribute more energy to Golomb.
So, I mean, do you reach the chemical equilibrium ratio?
Yes. Let me. I think I have plot for that one. Right. So I mean, if you check just for the free gas case, right? Because you have 3 flavor of quarks, then you have NC for each quark. You have NC color factor. You have spin 2. Then it's already like a 2 times NC times 2 times NF. I mean, NC equals 3 and F equals 3, this is already big factor. Then, of course, you have to consider whether it's boson or fermion. There's also some difference. I think you get some classic distribution. Now, what we show here, I use the temperature for final thermal equilibrium. But it's intriguing is, I think this really thermalize at the temperature T star to the when this self-Coulomb number is still less than in this stage, because you have the of the hard energies here. Time we do see these 3 halves, but this really rapid state, the third state actually really rapid. Then, well, because we don't have. I mean, the F0 is not small enough anymore. Right, then just more about the bottom up. If bottom up means, but actually, if you have quark, actually, because quark production is so slow, right? Equals 10 to minus 4, you don't see the bottom up. But you will see it if you go down F0, go to the 10 to minus 6. So here I just show you the bottom up, but it basically just try to confirm the parametric estimate. In reality, you don't have to go here. Okay, then what we also check is actually for F0 larger than 10 to minus 4, you always see this top-down thermalization, in the sense that your Coulomb happens in the late stage of your evolution. So actually, your Coulombs will establish thermal equilibrium first, then, but this temperature is still higher than the thermal equilibrium temperature for the whole system. Then actually this Coulomb temperature will decrease towards the thermal equilibrium temperature. Then in the meanwhile, you will see the quarks are produced. Then the quark will approach to the Fermi-Dirac distribution. But if you see the late stage, actually the Coulombs are almost always stay in thermal equilibrium. So this relates to the chemical equilibrium, etc. Okay, so this I just idealized the whole case, right? So this also makes the calculation simpler relatively. You can really go to this detailed checking. So I just say, okay, I did some study in a fixed box. The Coulomb number is really large. Then I go to some other limit. So we say, okay, this would correspond to the impending case, but at the late stage, now the distribution is really low. So actually, so for the same set equation, one can really just include one term like this one to capture the expansion. So this equation works if you go to the z equals 0. Then actually, this just take into account the effect that if you have a parton, if your momentum, your pz is not 0, but because you stay at z equals 0, right? Then this particle will run away to the other rapidity, right? So to the other part of the system, because you see that at z equals 0. So as long as you see that z equals 0, so you can use this equation. Then in order to get property from other rapidity, you just make a Lorentz boost, because f is a scalar. Right. So then, so one can really capture the effects of the expansion. So if you drop this collisional term, actually you get some called free stream solution. So in this case, the solution is exact. So the distribution at late time just given by the initial distribution with the combination pz times t divided by c0. So this tells you, as I told you, right? So if you have some particle with finite pz, it will run away to other system. So actually in this longitudinal boost invariant case, actually your typical, if you only consider the expansion, actually your typical value of the pz t. Well, yeah. So this information it just help you to understand the difference between expansion. I will not. I don't think we have time to really explain how you get the parametric result, etc. But actually, this is the first so-called. Really, this is the bottom-up paper. This actually start kind of the whole everything. I mean, in the last 2 decades about this kind of study. So they first work out this kind of parametric estimate. So you just unfortunately I don't have time to really show all the details how you do this kind of estimates. Then, but actually, quantitatively are really similar to what we discussed in the two cases. For the first case, so because initially the distribution is higher than 1, so we may consider this to the overpopulated case we started in physics box. Then they do see this self-similar solution. Actually, they have some really hard, really detailed numerically confirm, okay, they have this self-similar solution. Then actually loss power also at the third P with pressure of the house, and this trace but the finish. Alex Cook is PL. In this that the I think怎么游戏 consider I think I will simplest is that I just simplified case mission. The distribution this is给 initial 好 combination is actually the device. Then from we can balance if dynamic to theory, but here you have dynamic. Just in space. But this will be thing. Imagine way. But was scale particles theory too, right? Yeah, since there is still belong to goes to hydrogen. Dynamics the we took the opacity. Yeah, so you have linear response. We try you can have different glass. Refer how some also try, but what smaller linear kinetics. In this year, simple show KT in this one can see similar behaviors. Here I show PL over epsilon. If you remember, I showed in EKT, not in EKT, in the bottom up. So this is PL over PT. So it goes down and level off, then goes up to this basically hydro. Then in this simple theory, so you have similar behavior. So go this over epsilon, but epsilon equals basically PT plus no, PL plus 2 times PT, right? So then, so it has really quantitatively similar behavior. But here actually there's another concept I just tell you, and if you're interested, you can look up. It's called attractor. There's discussion. I mean, somehow since this kind of behavior is independent initial condition, etc., so people try to discuss the attractor. But that's not my main point. My main point is, so if you look at other theory, right? So for example, you have hydrodynamics, or you have this ADI-CFD correspondence, then the late-time behavior is basically the same. It's approach to hydro. This is really determined by the equation state, right? But at earlier stage, for different theory, so there's different contributions. So all these studies about pre-equilibrium things. So most people are focusing on this more like a theoretical understanding. But if you go to small systems, you can really probe because as I show you, actually for smaller gamma head, as I showed you before, this means for smaller systems, actually your non-equilibrium contribution become larger. So in this sense, if you go to the small system, actually, if you have theoretical calculation for this pre-equilibrium, now maybe you shouldn't call pre-equilibrium because in small system there may not be hydro, right? But this kind of non-hydrodynamic contribution, so can show up in the data of small system. So that's why, yeah. So I think this could give us some experimental testing of non-equilibrium calculation. Yeah, this just the same point, right? So if you go from large system to small system, now we have data for all the way two. Then, but this actually means the non-hydrodynamic contribution, right? Non-equilibrium contribution becomes larger and larger, and actually the hydrodynamic equation becomes smaller relatively. Then in this case, you may really put this kind of discussion about hydrodynamization, etc., onto the test. Then of course, one need to do more in this EKT and beta, which are mainly used for this kind of theoretical discussion in large systems. Okay, thanks.
Thank you very much. So, questions? Yeah.
Can you go back 2 slides? I think that makes 2 or 3 again. Yeah, no, this one, yeah.
Yeah.
Why? So when the size becomes larger than the free path, why don't you go to ideal hydro? Maybe it's like
no, because in this theory, I didn't show. In this theory, you can check the eta, right? So then this issue is whether this eta could really go down to 0 or not. I think, yeah, it needs really the much larger gamma head.
if you do a simple like billiard ball calculation.
Right.
So well, I don't know what it is. What you just take, and then it pretty goes
Really fast.
Your head is very quickly.
Probably you should go to this side, not ideal. The data is finite for transport. I mean,
If you increase the system size, it becomes.
No. I mean, the same one, cross section is finite, and density is finite. System size, I mean, data doesn't depend on system size. So if you approach hydro, but hydro at the corresponding data,
Right.
Shear viscosity there.
Yeah.
If they increase the cross section to a very large value, then it would supposed to be should approach ideal, but not at given cross section.
Right. I think it's mainly the gamma head. I mean, if it is gamma, so what you say is true because the eta will inversely proportional gamma, then right. So if gamma goes to infinity, obviously the eta OS will go down to 0, then it should be ideal head, right? But this combination, the gamma could be finite. This means that the eta OS could not be 0, even for larger system.
Eta OS is basically or eta, right?
Right. Eta OS Right.
T over sigma.
Right. Eta, yeah. Eta OS will be inversely proportional to gamma up to some other factors.
You mean your gamma compares this gamma?
No, we have gamma and gamma hat. Gamma is the coupling, which actually enters the
Yeah. So your
yeah.
gamma. So your gamma is a representation of sigma cross section, you mean?
Right.
Yeah.
Right.
So it's I mean we know right from
Exactly.
yeah it is T over sigma, but it has nothing to do with L with the size.
Right. So I agree with your argument. You just said yeah.
Other question?
You have expression for the by screening math and the two tabs according to the so this essentially also works for non-equator.
Right. So you just
This works for weak coupling case and medium order.
right. Exactly. I mean that's why I only stay in the limit QS much larger than QC. I never really directly go down to the realistic case. I mean, yeah. So all this also the quasi-particle approximation one has
Right.
to check, right?
Okay. Any other question?
Everybody is confused, I guess. I mean, you can speak Chinese better.
Right, you can also speak Chinese.
Yeah, any question.
Any question is welcome. Okay, so we know that yeah, thermalization is very intriguing and interesting phenomena, not only in heavy-ion collision in quark-gluon system, but also in actually many interacting many-body system, right?
Right.
So can you also give some comment from your perspective studying the quark-gluon matter thermalization, the thermalization in other systems like maybe cold atoms, mass matter, or cosmology systems?
Right. It's a really good question, but it's obviously a big question. But I think one, as I already mentioned here, is for example, this called the universal scaling or the non-thermal peace point. Actually, there has been studies which shows actually this kind of behavior also shows up in cold atom, and also in other like cosmology or something, as long as there really large occupation of the fields. So this is also this actually relates to something called turbulence, and yeah, if you think about like fluid dynamics, there's really turbulence, then they can also have this kind of similar behavior, etc. So I think even though we are focusing on the Havan conditions, but as I show you about this path integral approach for fields, actually all what we are studying here could be also applied to other system, right? So and also like what like Derek Pinney showed us. So actually from our field Lagrangian, actually we can go to some universal exponent. We can calculate the universal exponents. This could apply to, for example, the chiral symmetry breaking, but the same exponents could go to other condensed matter system or cold matter system, etc. So I think everything we need to learn more from other fields, but actually what we are doing here are connected with other fields in this sense.
Okay, thank you. Thank you. Any other question? Okay, so if no further question, I think let's close this session and thank Professor Wu Bing for these two very nice lectures. So with this, we have had all the lectures of this summer school finished. So in this afternoon, China Normal University. Okay, let's go for lunch and see you in the afternoon.